as an educator, my goal is always to inform, to inspire, and to incite. Okay, now let me clarify. I want you to learn something you maybe never knew before, but I also know that people generally do not change their behavior based on facts. That's true. Okay. Just watch television commercials and political ads, and you'll learn that people generally make decisions based on how they feel about something, about emotion. So I think it's important that there's facts that you'll learn that you didn't know before, but that it'll be woven into some form of inspiration, and out of that would come application. I use the term insight because insight implies action. And so hopefully by the end of this session today, you will feel confident enough to talk to people who call in or send emails or whenever you're volunteering, have questions about gardening, that you'll be able to use this botanical information as a base for answering those questions. I'm much more interested in that you use the science of botany and horticulture to solve problems rather than say, what does control aphids? And that there would be one answer, all right? Because invariably, as soon as you know that this is the answer to that question, someone's going to ask that question in a different way that answer will not apply. Make sense? Okay, so are you ready?
Yeah.
Good, because I'm ready too. So I'm a fellow gardener. I've gardened in the same spot for 41 years. My wife and I bought this little starter home, right? And I think we're going to finish there. So here's the good news. That means I killed all my plants in the same location. Seriously. It's a 1/4 acre lot in North Raleigh. This is 1 year's iteration. This was a good year. Okay. You notice I did not show a slide of a bad year. Okay. But I have them. All right. And so here's what I've learned. I've learned that the average American lives in a home for 7 years before they move. Okay. Now, I don't know about you, but as a gardener, 7 years is no time at all in the life of a plant. Right. And so I've had the ability, and what I bring to you is a experience of continuity, in that I've been through numerous iterations in my own garden that have taught me about the way plants grow. All right. And so that's just a little bit of background. As Master Gardener volunteers, there's a whole lot of importance in understanding how plants grow. I am convinced, this is a personal conviction based on my own research and whatnot, I am convinced that plant failure is caused by two factors. One, poor light relations. In other words, humans' inability to understand how light influences plant growth. All right. And as a result, we put that plant in the wrong place. And more than 50% of the calls or the questions you're going to get as Master Gardener volunteers are going to be, I have this plant and it's failing. And your first question is going to be, what kind of plant is it? That's a challenge. Okay, most of the time when someone says they have a plant failing to me, I'll say, what kind of plant is it? And they'll say, well, it's green. So we have to be ready for these little curveballs that come. Okay, but invariably, much of the challenge and the death come from a poor understanding of how light influences plant growth. So guess what? One of the things we're going to talk about today, how light influences plant growth. Okay, and you might say, oh, this is going to be just like a botany class in college where I'm going to learn photosynthesis. Yes, we are. We're going to learn it in an entirely different way, in a holistic way, and not in a box way. All right. Secondly, I'm also convinced that the other half of the problems are caused by soil issues, a poor understanding of how soil influences plant growth. And I've got some examples to highlight this and how important it is to be very well aware of the soil. Now, we do not have time because this is about botany and soil is really soil science. But there's a whole idea when it comes to
You were
because my
okay.
wife
Sure.
says I'm way too loud. Okay, so anyway, those are the two areas where I think you can always kind of direct back to, oh, there's your problem. You don't know enough about how light influences plant growth, or you're really unaware of how the soil. Now, you see the parenthetical two areas there. Okay, those three areas, sugar, water, nutrition, are incredibly important when it comes to the scheme of things when it comes to plant growth. I'll never forget when my first daughter was born 40 years ago. My first question to the doctor was, what do they need to grow? Right? I was concerned. I wanted to make sure she had everything she needed so that she could grow. Okay, as plant parents, we need to be asking the same questions. All right. Now, what results when these things don't actually jive? It results in increased cultural problems, which is why gardeners are so concerned because gardeners are way more concerned about culture than they are about environment. All right. And oftentimes we need to be asking the question, when I go to the doctor and I say, my elbow hurts, okay, what can I do to fix my elbow? Their first questions out of their mouths are, what have you been doing lately? Where have you been putting yourself? Okay, environmental questions. And yet in gardening, if my plant starts to fail, it's like, what do I have to do to make it better? And what are the knee jerks? The cultural knee jerks. Fertilizer and water. No, pull it out. Okay, there is a pest, by the way, there is a pest management, we're never going to get through this. There is a pest management technique that is 100% effective. It's called planticide. Okay? That's right. If I have a plant that is succumbing to an infirmity and I'm not emotionally connected to that plant, I remove the plant. 100% effective. I'm not going to have any more infection. Consider that. All right. Anyway, pest issues, fertility, maintenance, plant replacement. These are all things that ultimately go up and get expansive when these things don't work. All right. So botany. Botany is a pure science. Horticulture is an applied science, right? And so a botanist loves plants because they're plants. A horticulturist loves a plant because it can do something with it. It may serve humanity in different ways, whether we can eat it, look at it. It reduces erosion. You hear the difference? One's an applied science, botany being a pure science. And so what are we talking about? We're talking about things like taxonomy. Taxonomy is really talking about how things are classified, how they're categorized. All right. Nomenclature, names. Oh, that's always a fun one. And if we've got time, we'll talk a bit about that. Anatomy and morphology. We're talking about the parts and how they fit together. Right. And then the one that always scares everyone is this word physiology. Okay. Physiology is not that complicated. If you consider that the term physiology means what's going on inside. What's going on inside? That's all physiology is trying to figure out what's going on inside. All right. And there it is right there. So with that, we start talking about botany, and we're going to talk about plant growth. We're going to talk about the physiology, right? That's going to be our first section this morning. So the first question I asked the doctor was, what does my kid need to grow? We need to be asking the same question when it comes to plants. What's necessary for plant growth? Okay, there's 4 things necessary for plant growth. Water is one of them. Shoot, plants are typically somewhere around 78 to 80% water. All right. Nutrition. There's a certain level of nutrition. Now, y'all, you got to make sure that you understand the difference between nutrition and food. And sadly, social media, the evil of social media transcends gardening as well. In other words, if you read things on social media about gardening, you should believe them just like you believe all the other stuff that's on social media with great reservation. All right. And sadly, in gardening, we have replaced the term nutrition with the word food. That's why when you go down to the local garden center and you look at bags of nutrition, it says plant food. They are lying. That's not plant food. All right. And so we'll talk about some of the things that makes plants so unique from human beings. And one of them is this nutrition food thing. So we'll get to that. That's something to look forward to. All right, next one, sugar, glucose. Okay, the basic building block of life is glucose, sugar. All right. And sadly, there are so many misconceptions about sugar and nutrition when it comes to plant growth. And if we can get those organized in a way that we understand them, we can solve lots of people's gardening problems. All right. And last but not least is chemical energy. It's the very energy that is keeping your eyes open and making your fingers right, or your fingers type on the keys. That's the energy that organisms need to do work. All right. Plants need all 4 of these, all 4. Water, nutrition, sugar, chemical energy. Okay. Why? Okay. This morning I'm going to ask you to ask why a lot. Because I just don't want you to say, oh, okay, they need them, but to say, all right, well, why? Well, water, obviously, I already said plants are made up of 75 to 78 to 80% water. So to stay hydrated, okay? Anybody here suffer from dehydration in their lives? It's not a fun day, is it? Right? Okay. Consider plants that are dehydrated cannot physiologically function just like we can't physiologically function. And water is a very, very, very big player in this plant growth process called photosynthesis. Make sense? All right, we're going to get to that. Next, nutrition. What do we need nutrition? Okay, overall plant health comes from a hearty amount of nutrition within that plant. Okay? Just like in humans, our health is often a reflection of how well nourished we are. If we are malnourished, then we suffer, our physiology suffers, right? Not only that, but nutrition plays a major part, guys, plays a major part in putting compounds together. Necessary compounds that help that plant grow. Why sugar? Sugar is the basic building block of plant growth. A plant cannot make a leaf without a savings account filled with sugar. All right? You cannot build a leaf on credit. That's a big difference than in today's society. I'm digressing. Hold on. All right, building blocks. Not only that, but much of the sugar that plants produce don't even get used as building blocks. No, they go into the wood stove. Okay? They become those sugar molecules become the fuel that supports the chemical energy, which is the energy a plant needs to make that flower. So see this flower over here on the right? This flower requires water, nutrition, sugar, and chemical energy in order to be formed. All right, so that's why we need all four. And then we just need to figure out where the four come from and how we as gardeners can facilitate those four things coming together to create good plant health. We've already mentioned this. So you got a plant, it's not growing well. Typically 95% of all phone calls to extension offices are, I have a plant that's not growing well. Help. So you're the sacrificial lambs who are going to answer those questions. Plant not growing well? Well, it's not flowering much. Maybe you're not getting any flowers, maybe no fruit, maybe just a few small fruit. I always find myself saying when I'm growing tomatoes is, why don't they look like they look on the tag? Right? Y'all are shaking your head because you've been there too. How do we gardeners respond? What's the knee-jerk response to when things don't grow well? Yeah, we water it because we think maybe it needs more water, okay? Or we add fertilizer. Those are the two cultural things that typically we do right away. We don't even ask questions. We just go, oh my gosh, I got to water and fertilizer. Just understand that you cannot fertilize a plant into submission. You can't fertilize a plant into growth just because you want it to grow by fertilizing it. Dry weight. In horticultural science, in a lot of biological sciences, when researchers do research on treatments to determine which treatment results in a better result, results in a better growth. In the case of plant scientists, okay, we'll apply a certain treatment to this group of plants, apply a certain treatment to the same type of plant, different group, and then we'll try to assess which treatment results in more growth. How do we measure the results of the two treatments? Well, we scientists, what we do is, first of all, we treat lots of them the same way. And when we're done, we harvest them all, right? We harvest them all, and we clean off all the soil on the roots, we rinse the roots off, then we take all those plants and we put them in an oven. Not the kind of oven you cook in. It's called a plant drying oven. You put it in there and you leave them in there for a week. And it takes all the water out of the plant. So what's left? Dry weight, which represents the what? The stuff of growth, right? We take water out and we go, okay, now we can measure the weight of that plant that's been dried and actually have a number we can assign to how much growth happened based on that treatment. Make sense? Okay, so here's the question. How much of the dry weight of any plant comes from the photosynthetic process that the sun drives versus how much of the dry weight of the plant comes from nutrition out of the soil? Any guesses?
Mostly sun.
Mostly sun? Give me percents. What do you think?
50-50.
50-50. God, that's a good way. Very good. Somebody's always going to do 50-50, and I'm happy about that. No, it's not 50-50. Someone else. Yes.
Oh, 70-30?
Which way?
70 sun, 30 soil?
70 sun, 30 soil. Okay, another?
60-40.
60-40.
Sun, soil.
60-40 sun, soil.
30-70.
30-70. 30 sun, 70 soil. Thank you for participating, but you're all wrong. Take a look. Soil, sun. 4% soil, 96% sun. Yeah, I was hoping. In the shower this morning, I was going, I want him to go, wow, when I show him. But it's so counterintuitive when you think about it. Now, first of all, let me say this, just because it's only 4% doesn't mean that it's that much less important to plant growth. Y'all hear me? My wife and I, remember the little house we bought? It was so little that when my girls got to be teenagers, both girls got to be teenagers, we either were gonna move, we're gonna kill them, or we were going to build another room to, so we wouldn't have to live with them all the time. So we went to build a sunroom. And so what did I do? Well, like first thing we did was we bought all the ingredients for that sunroom. We bought the doors, the windows, we bought the 2x4s, all the building blocks. Okay, that's all from the sun. And 96% of that sunroom was building blocks. 4% were nuts, screws, and nails. Could I have built that sunroom without those 4% nuts, screws, and nails? No, I have just a pile of building blocks. All right, so just because it's 4% doesn't make it that much less important. They're equally as important. However, when you look at this, you then got to start to wonder why, when a plant's not growing well, we do this to it as a knee jerk. That doesn't make any sense. It's like, oh, it's missing some of the 4%. Well, that may be true, but typically, if it's a 96%, 4% difference, remember what I said at the beginning of this morning's session, just a few minutes ago, most failure occurs because of a lack of understanding of how light influences plant growth and how soil influences plant growth. That covers 100% of all the plant growth. But it's this kind of a balance, right?
It'll go away.
It'll go away because I touched the screen. Thank you. Okay. So what is a plant made up of? Well, plants are made up of tissues, all right? Tissues that contain water, sugars, nutrients, and other compounds. Did you know plants make hormones? Okay, just like people have hormones, plants have hormones. Doesn't make plants moody, but they do. They do have hormones that influence their growth. Okay. Is it sunny where you are? I'm not sure. Full sun, according to, I've gathered up all kinds of information about what does full sun mean? Because you go into a garden center and says, what does that plant need? They go, it needs full sun. What's that mean? Okay. Well, the best I can come up with is full sun equals a minimum of 6 or more hours of direct unimpeded sunlight. So shame on any gardener, myself included, who will take a plant where it says full sun on the label and put it in an area that gets 4.5 hours and go, it'll be fine. All laughing because you have all done it yourself. And you're going to talk to a lot of gardeners who do it all the time. And then they say, I don't understand why it doesn't look like it looks on the tag. And you say, what does the tag say? The tag says full sun. Do you have it in full sun? And there's a pause on the phone. Now you know what the problem is. Anything else is considered partial. Partial what? Partial sun, partial shade, full shade, all these others. And sadly, we have not come up with, the horticultural community has not come up with a way to quantify all those terms. And so we have to go on experience and hearsay as to what full shade is and how that is different from partial shade. Plant growth processes. This is where we're headed this morning before our first break. We're going to talk about how plants absorb things, how plants move things, how plants make things, how plants need help making things, and how plants use things. All right? Those are the 5 processes of plant growth. Now, here's the problem. I don't know about you, but when I was in high school and college, anytime I got into a botany section, okay, no one ever taught me holistic plant growth. No, what's the first day of the first lecture when you get into the plant unit in 10th grade? They throw the photosynthesis equation up there. All the kids go, ugh. Right? And they say, this is plant growth. Well, it's not. It's 1/5 of plant growth. It's one part of plant growth. Very important part, nonetheless, but it's not going to happen without these other processes. All right? So I maintain, in fact, I didn't even start understanding all of this until I was told, teach plant growth. And it was like, oh, well, you mean photosynthesis? No, teach holistic plant growth. And so that's why I'm referring to plant growth processes, as these 5 contribute to what we know as holistic plant growth. Okay, so let's talk about absorption. That's the first one. Number 1 absorbing organ is the root. Stop worrying about how much water or nutrition is absorbed by the leaves of plants. That's so minuscule, it's not worth talking about. Unless, of course, your daughter's getting married in 2 weeks and you want to green up the shrub. Then you can take a fertilizer in liquid form and spray it on the green leaves, and it'll absorb enough to change the color of the leaf. All right, but typically speaking, we're talking about a significantly higher amount of absorption that occurs in the roots. What gets absorbed? Two things. Water, oxygen. Water and nutrients, okay? Water, passive process. We'll talk about what that means. Nutrients, active process. So here's the thing. When water comes into the roots, nutrient elements are not riding those water molecules like you'd ride a horse. In other words, they're not riding those molecules into the roots. It doesn't happen that way. Water moves in freely, and nutrients have to be taken up by the root system. That's why there's a difference between passive and active. Good absorption is dependent on good soil building practices. So we'd have to have a whole unit on how to go about building good soil. And by adding organic matter, we can improve that soil so it will be a better provider of water and nutrition. Here's something that Bartlett Tree announced about 35, 40 years ago. Roots grow where there's water and oxygen. Notice it doesn't say roots grow where there's fertilizer. We got to stop fertilizing plants, everyone. We got to start monitoring and adjusting nutrition in the soil. There's a big difference between those two statements. All right. And all too often, sadly, our own market teaches us what? Well, here's evergreen fertilizer, here's cactus fertilizer, here's, this kind of fertilizer. It's teaching us to what? To fertilize plants. We need to be more concerned about, is the soil environment in a position to provide nutrition to the plants that are growing in it? It's a totally different mindset. Okay, so you ready for some chemistry? Ready to break out in some hives? The other thing about roots, we don't have a lot of time to talk about this, but plants have three kinds of roots. They have anchoring roots, transporting roots, absorbing roots. Guess what anchoring roots don't do? They don't absorb. Guess what transporting roots don't do? Absorb. That's why transporting roots are underneath the sidewalk. Because there's no water underneath the sidewalk. They can't absorb anything, and that's okay because the roots that absorb are the absorbing roots. And guess where most of them are located? On the soil surface. Why? Because there's more oxygen on the soil surface than anywhere else. Does that make sense? All too often we worry more about the anchoring and the transporting roots and we really need to be concerned with the absorbing roots. In any kind of development, the topsoil, which is a combination of clay and organic matter, all right, is generally scraped to the side because good engineers build houses on subsoil. That's what it's called, subsoil. A B horizon, not topsoil. All right, guess what doesn't grow in subsoil typically? Absorbing roots don't grow in subsoil because they don't have enough oxygen. All right, so then what happens? The house gets built and the builder sells all the topsoil to a subdivision they built 2 years ago to people who don't have any topsoil, right? And then they take the turf, then they take the sod and they put it down on top of the subsoil, and that's why it needs to be irrigated and fertilized ad nauseum, then aerated, and because we haven't prepared that bed for good plant growth. Here we go. We're going to talk about absorption of water. Envision a rubber box. And this rubber box has a membrane. It has a screen, much like a screen on a screen-in porch, between the two sides. We'll call this A, we'll call that B. All right? And we refer to that membrane. I mean, if you have a screen-in porch, you have a semi-permeable membrane. Semi-permeable membrane allows water to move freely back and forth, but not anything that's dissolved in the water. Does that make sense? Okay? So you got this semi-permeable membrane, you got this rubber box. Okay? Now, before I put that up there, I'm going to take a salt shaker from my kitchen table, and I'm going to shake 10 shakes here and 5 shakes on the other side. Whenever you take something that dissolves in water, it's called solute. Solute. And so if I have 10 shakes on the left and 5 shakes on the right, which one's saltier? The 10, right? The one on the left, okay? Which one has a higher solute concentration? The one on the left. Okay, good. So solute concentration equals the salts that are dissolved in solution. Okay, and those are ions, but don't worry about that. Just worry about solute concentration. So, I lied. I messed up here. So I shake 5 shakes on. Some of you are worried about how big the shake is. The shakes are all exactly the same amount, okay? So don't go, I'm not so sure he was shaking hard enough. All right, and on the right is 10. Which side has a higher solute concentration? Right side. Which is less salty? Left, okay? So here's what we know about water. Water is like Jimmy Carter. Remember Jimmy Carter, our president? Okay, Jimmy Carter, he's still alive, and after his presidency, he was known to be able to go to incredibly salty situations and diffuse those salty situations. He was a wonderful, wonderful peacemaker, right? Water is a peacemaker. Water is Jimmy Carter. Water is always moving to a saltier situation to diffuse it. Does that make sense? All right. So without even doing anything, if I set up this concentration gradient, right, which way is water going to move without any help from me? It's going to move from left to right, and 10 will now be diluted down to 7.5, and 5 will now be concentrated up to 7.5, and it'll reach this thing called equilibrium. I see some of you were awake during chemistry. All right. Water moves that way. And that's what we call osmosis, the diffusion of water across a semi-permeable membrane from an area of lower solute concentration to an area of higher solute concentration. When I took chemistry, that's all I got. I didn't get the rubber box. And therefore, I didn't understand osmosis. All right, not only that, but the chemists are very strange people. There's probably somebody who's in chemistry here who's alienated them. But I was given the definition of osmosis as the diffusion of water across a semi-permeable membrane from an area of high water concentration to an area of low water concentration. I did not understand that. From a standpoint of less salty, more salty, it made much more sense that water's going to move to a more salty location. Now, y'all are looking at this going, so what, Bryce? This is how plants absorb water. This is how plants absorb water, okay? Look, a plant. This is my incredibly artistic schematic diagram of a plant. There's the soil, those are the roots, all right? Soil scientists at NC State define soil as stuff plus space. It's the solid materials plus the space that is created by the solid material. Stuff plus space, all right? And in the space, some of it's water and some of it's air. And the water portion of the space is called the soil solution. And it's very important because guess where absorbing roots absorb all the nutrition from? The soil solution. But a root cannot yank a potassium molecule off a soil particle. A root can only absorb potassium in the soil solution. So the root has to be connected to the solution. Make sense? All right, so that's what we've got here. We've got a soil solution down here, okay, the liquid fraction of the soil. And this is my best bet at blowing up a root. I don't mean kaboom. I mean, let's zoom in on it. Okay, there's the root. Those are individual root cells. So a root is made up of cells. What's a cell? It's a little rubber box with water inside that has stuff dissolved in it. So we can go in and we can measure the solute concentration of the roots. And guess what? It's 10 under normal condition. We can go into the soil solution and measure the soil solution concentration, and it's 5 under normal condition. So you tell me, which way is water going to be inclined to move? Into the root, okay? Especially when the leaves, and I didn't draw the leaves, but you can imagine the leaves there. Every day when the sun comes up, the leaves start using water. And so they're using water and they say, hey, send up some more water. And so water is translocated. It moves up through the plant, right? And then is used up by the leaves. So as long as the leaves are using water, the 5 goes into 10, but this doesn't get back down to 7.5. What happens is the water then moves up, keeping that concentration gradient alive so water continues to move until the sun goes down. And then when the sun goes down, the whole system comes to equilibrium, and then this goes to 7.5, and that goes to 7.5. It's a self-regulating system. So somebody tell me, how much energy did the plant have to expend for this to happen? 0. This is a passive process. This plant can absorb water all day long without ever expending any energy. Isn't that cool? Yeah. I think it's great. Okay. So if you're paying attention, in your head, you're going, well, give me a practical application that I could use if a gardener calls and says, what's going on? Well, here's the practical application. We Americans, typically, if we read on a bag that 1 handful is good, 2 handfuls is even better, and then I'm walking away doing a little right there. All right, more is better, right? It's always better. Okay, but there are right reasons why the fertilizer recommendation says only a handful for a shrub this size. So let's say you put down too much. Uh-oh. What's going to happen? Oh, look what it does to the soil solution. As those nutrients come out of the fertilizer, as they dissolve, okay, it's going to drive the solute concentration up, and in this case, it's going to drive it up to 15. Now what do we have? We have a problem, because which way is water going to move? Out. The leaves are still doing their thing. As soon as the sun comes up, hey, I need more water. And there's no more water to be had because it's all exited, right? So where's the first place we see anything happening when this kind of a situation occurs? First place, at the leaf. And guess what the leaf does? First thing it does is wilt, and then the margins start to turn brown. And you know what we call that? Listen, you know what we call that? It's called fertilizer burn. I used to think fertilizer burn was when too much fertilizer went into the plant, up in the leaves, and burned the leaves. No, fertilizer burn is nothing more than the plant drying out at the point of need due to a wrong solute concentration. All right. So somebody calls you on the phone and they say, I fertilized all my azaleas in the backyard, and my neighbor came over and asked me how much I put down. And I put down 3 times as much as what was recommended. And they freaked out. And they said, you put down too much. What do I do? Can I do anything? You say, well, can you scoop up the fertilizer? No, I scratched it in.
Water.
What's that?
Water.
How do you know that?
Because
Because you now understand how plants absorb water. And the fact that you understand the principle, you can solve the problem. Okay? What do? You pour copious amounts of water on the soil, driving 15 down below 10, reverse the water movement, and you've averted the fertilizer burn. All right? Now that's the good news. What's the bad news? All that water that you poured in to lower that water continues to move down through the soil, called leaching, because it takes with it all that extra fertilizer that you put on. Shame on you. Now all that extra fertilizer goes into the waterways, lakes, and streams. Guys, there's a reason why there's a recommendation on the bag. It's not just a good idea. They've done research to determine how much you can put down before you're going to change that osmotic relationship with the plant roots. Okay? So that's how we get absorption. Now, I'd love to tell you that nutrients just climb aboard a water molecule and woohoo, ride it in. I'd love to tell you that that's the case, because then we could say nutritional and water absorption is passive. But sadly, it's not. Water, passive process called osmosis, diffusion of water across a semi-permeable membrane from an area of lower solute concentration to an area of higher solute concentration. Fertilizer burn. So that's just what we depicted with that. Nutrients. What's that? If you're worried about me, don't.
No,
I mean, help them, yes.
You're trying to blow us.
I'm just a sweater, that's all. Yeah. I sweat in a snowstorm, my wife says. So what's that? It's a forklift, right? Some of you are worried about saying it. It's like, where is it going? It's a forklift. And you know why the fork's on the front? Because it has these 2 things that come out, and then only certain things, it can only pick up certain things on pallets, right? Slides into a pallet. That's a forklift. Okay, what's that? That's a forklift. But it has a different attachment on the front, and it's specific for some other kind of unit it can grab. What's that? That's a forklift for tires. Okay, that's what the attachment is there. And what's this one? This is a forklift to carry toxic waste around. Okay, barrels. Each and every one of this is fueled by some kind of a machine that uses energy to carry the stuff around, yes? Okay, that's how plants absorb nutrition. In the membrane, that semi-permeable membrane that surrounds the root, there exist these little tiny forklifts. There's one forklift for nitrate, there's another forklift for potassium, and each one of those has a separate attachment that matches up with that specific nutrient, right? So what happens? Forklift goes over to the edge of the roots by the soil, and the potassium, say I'm a forklift for potassium, and then the potassium molecule sees me, highly attracted to me, comes moving over. I can put my whatever fork into it, lift it up, carry it across the membrane, and I deposit it in the cell. But I have to burn some fuel to do that. So what do we call a process in a biological organism that requires the expenditure of energy? It's called active. It's an active process. Okay. Right now, the most agreed upon theory for nutrient uptake is something called the carrier molecule theory, which basically says there are these little forklifts that are species specific for different nutrients that carry the nutrients over. Here's what we know for a fact. Plants can't absorb nutrition without expending energy. Make sense? So you should be asking, where does the plant get the energy to do that? They don't have little propane tanks on the back of the little molecules, right? Oh, there's another one, paper reams. When I was doing my research, I was amazed how many different attachments that forklifts can have. It's quite amazing. Carrier molecule theory. Nutrient-specific molecules responsible for nutrient uptake. Energy must be expended. That's what we know. It's active transport. So I'm going to leave you hanging. Where does the plant roots where do they get energy to be able to do this? Because in order to absorb nutrition, the plant has to have available energy. Right? That's rhetorical. Don't try to answer. That's absorption. Any questions? Y'all were locked and loaded. That was great. Thank you for paying such close attention. Second one, much easier. Translocation. What's translocation? The movement of materials from one location to another. It's that simple. Seeing that most of our garden plants, if not all of our garden plants, belong to a division within the plant kingdom called Tracheophyta. Okay, Tracheophyta, plants with tubes. All right. Then we know that materials get moved in through the plant through a series of cells that create tubes. All right. And this shows you by direction and color the different tubes that are responsible for translocating materials. We know water and nutrients move upward because the source of water is downward. Okay, water nutrition moves upward through a series of tubes, and we know that sugars move down and up. This is kind of funky, but a lot of sugars that are made in the leaves move down, but sometimes they have the capacity to also move up. Make sense? All right. And somewhere in your history, you've heard of the famous xylem and phloem tissue. Please don't try to draw this. I even tell my own students at NC State, don't try to draw this. What I'm trying to show you is that the tubes are different for the different materials. Water and nutrition through the xylem, moving upward. Phloem vessels, okay, moving sugar downward and also laterally and upward as well. But typically it's a downward flow. We call that the vascular tissue, and any vein on a leaf is a representation of the vascular tissue. Make sense? All right. And I like to do a little magic trick with third graders. Well, I'll take a dogwood leaf, and because the vascular tissue, the xylem and the phloem, is so fibrous, I can break it like that. They're not looking. I break it, and then I come around like this, and it makes it look like it's suspended underneath the top part of the leaf. They all go gaga, and now I've got a new gardener on my hands. Okay? So that's translocation. It's just the movement of material. You see what we're trying to do? We're starting with absorption, how the stuff gets in. Okay, now how does it move? All right, and now we get to find out how the plant makes stuff. So you see how clever I am? I colored the photosynthesis in green. Yeah, that's so clever. Okay, I maintain that photosynthesis is by far the most important biological process on Earth, known to the world. You say yes because of the oxygen. I say no, and a lot of biologists and botanists say no. Not that plants don't produce oxygen, but the oxygen, listen to this. 100 years ago, our atmosphere had an oxygen concentration. Okay. Today, our oxygen concentration in the atmosphere is the same, less, or more than 100 years ago. How many say the same? Less. More. It's exactly the same as it was 100 years ago. Photosynthetic area on Earth 100 years ago, today. More, less, or the same? More. For every tree that gets cut down on this earth, 4 get planted. So look at all your confused faces, because we get on social media and it says we got to plant more trees because, here's the problem. The problem is not amount, and this is quite the same situation in society. It's not always availability; it's distribution. Okay. Why should we be concerned about deforestation? Because of the ecosystems that are being completely and totally destroyed by that behavior. It's not because we're going to run out of oxygen. The oxygen hasn't changed. There are scientists who believe that our breathable oxygen is a function of the ozone. Remember the ozone? Used to be a problem. Now it's come back, thank goodness. But that chemical reactions in the ozone are responsible for the oxygen balance in our atmosphere. Okay? So that doesn't mean that photosynthesis is not important for oxygen's sake, but it means that that's not why it's the most important process on Earth. So why is it the most important process on Earth? Food. Food. Why? Oxygen, yes. Plants make their own sugar. There is no organism on this earth that doesn't require sugar, and yet only a fixed number of organisms have the ability to make it. And those organisms are called plants. One of the greatest differences between a human and a plant is I can't make my own sugar. Take me to the beach, I get sunburn. Take a plant to the beach, it makes more sugar. And what I don't understand is why Hollywood has not taken advantage of the scientific principle to create superheroes that are photosynthetic. It just doesn't make any sense. One of the greatest superheroes would be Photosynthesis Man, right? Photosynthesis Man, this superhero who is fueled by the sun, and you know who its arch enemy is? Dark person, right? And dark person captures Photosynthesis Man and puts him in the basement with no windows, and he starts to dwindle. It's kind of like kryptonite on Superman, but in the case of Photosynthesis Man, it's darkness. I don't know. I've told my students many times, if anybody goes to Hollywood and starts being a screenwriter, all I want is a little credit in the bottom of the movie that says this was inspired by HS200 home horticulture. It's never happened. All right. Just a show of hands. How many of you have baked from a recipe? I've been involved with baking from a recipe. Okay. So you'll notice that the first thing I didn't do was put the equation of photosynthesis up there, because that's a big turnoff, right? But baking chocolate chip cookies, that gets everybody's attention. There's some really good cookies out there on the table that are delicious. Okay, now that I've mentioned that, we probably need to break soon. But nonetheless, I maintain that this photosynthetic process that is responsible for creating all this food for the world, for every living thing, okay, is no different than baking chocolate chip cookies. Right? So when it comes to baking chocolate chip cookies, and I've done quite a bit of research, okay, what's the recipe? What's the recipe? What's one thing you need? Okay, what do we call those things? Yeah, we call them ingredients. So we need ingredients. Okay, what else do we need? Well, before then, we need a mixing bowl. We got to take the ingredients and put them in someone and mix them up, right? Then we need a source of energy. In this case, it's heat, and it's provided to us by the oven. But we're missing one thing. If we have these three, we're missing one. We don't get chocolate chip cookies. What is it?
The combination.
It's something. The cookie sheet. No, seriously, look, this is what I've learned. I've learned that if you bake cookies and you put that cookie sheet with the dough on it into the oven, okay, the oven heats up the cookie sheet, and then the cookie sheet makes the dough change into a chocolate chip cookie. That's called a chemical reaction, right? It's not the air temperature that causes the cookie to be transformed. It's the air warms up the cookie sheet. Blueberry muffins. What do you need? You need a muffin tin, because again, the heat of the oven heats up the muffin tin. Do you know what we call that in science, where there's a place where the reaction actually happens? It's called the substrate of the reaction. That's the location where the reaction happens. And guess what? Baking chocolate chip cookies is irreversible. Chemical reaction is irreversible. Okay? I've done research on this. As a kid growing up, I'd help my mom. I'd eat half the dough, then she'd make the cookies. Then I'd want dough again, and all we had were cookies. So then I'd take cookies, put them in a bowl, mash them up, add milk, and then I had cookies floating in milk. I could never make the cookies go back to being dough. That's why it's a chemical reaction. There's transformation with the ingredients that you put in. Photosynthesis is a chemical reaction. It's not reversible. All right? Oh, look, there it is, chemical reaction. Okay? Not reversible. See, I got ahead of myself. Okay, so here we go. Photosynthesis. We got all these ingredients. We've got the mixing bowl. We've got the cookie sheet. And we have the energy source. That's photosynthesis. Now all we have to do is match up what are the ingredients of photosynthesis, what are the mixing bowls, what are the cookie sheets of photosynthesis, and then what's the energy source. Some are obvious, some are not so obvious. Okay, and that is just pure cruelty to you. Sorry. So now we get to the photosynthetic equation with the umbrella of baking chocolate chip cookies above it. All right. What are the ingredients? And before you answer, there's only two. Water.
Carbon dioxide.
Sunlight is not an ingredient.
Carbon dioxide.
Carbon dioxide. Water. And I always thought it was really cool. Water molecule actually looks like Mickey Mouse. I thought that's pretty neat. Carbon dioxide, and that's what carbon dioxide looks like. So really, what are we talking about ingredients? We're talking about oxygen, carbon, and hydrogen, right? In these different forms. Those are the only two ingredients that plants need. Do you think plants are happy about an increased CO2 concentration in our atmosphere or sad? If you were a plant and you had a brain, would you be happy or sad if these are the two ingredients? You'd be thrilled to pieces, right? And guess what? There are some plants that are more happy than others and have a greater capacity to absorb more carbon dioxide, right? Guess what kind of plants they are? Weeds. I'm not making this up. One of the best CO2 scrubbers, CO2 absorbers is poison ivy. Yeah, it's a sick joke. It's a sick joke. So those are the ingredients. Okay. Energy source. Light energy, okay? Not just sunlight. This light energy is the energy source for photosynthesis. May not be as effective or as good, but it does work. It's kind of like when I was growing up, my sister got an easy bake oven for Christmas, right? Which is fueled by a light bulb, right? Okay, it's not the best oven, but that light bulb could work just as well as a big gas powered oven, right? And made little tiny cupcakes. Little things like this. Anyway, I gave it back. Mixing bowls are the leaves, typically the green plant tissue where all the ingredients go, the leaves. Okay. Substrate of the reaction. What is the cookie sheet of the reaction? Where does the actual reaction of photosynthesis occur? This is so important for application. Yeah, it occurs in these little bitty organelles in the cells called chloroplasts that are filled with a green pigment called chlorophyll. Right? So what happens in Vegas stays in Vegas. What happens in the chloroplast stays in the chloroplast. That was a joke, but y'all didn't get it. So we'll go back to that. All right. In other words, if we don't have these green organelles in the cells, notice animal cells don't have them. Okay. If they did, we wouldn't have to rely on plants so much because then we'd be photosynthetic. You go to the beach for the weekend, you come back fat. Anyway, these organelles are where the carbon dioxide and the water go to be transformed. All right. So do you understand why? How green the leaf is going to influence how much sugar is going to be made. We'll get back to that. Chloroplast, and inside the chloroplast is this pigmentation called chlorophyll. Chlorophyll is nothing more than a solar panel that has the ability to absorb light and transfer that light into energy that's going to take the water and the carbon dioxide, mix it together to come out with our chocolate chip cookie. So this is what a typical chloroplast looks like. Don't worry, it won't be on the test. You didn't know you were having a test, did you? Okay. These are the solar panels. They stack on top of each other. Those are called granum. And then this stuff that's kind of spaghetti in between, those are called the stroma. And between the two, water, carbon dioxide are transformed into the products of photosynthesis. And this is another diagram of a chloroplast. Okay. Notice everyone, and we're trying to tie all these pieces together when it comes to plant growth. Notice that a chlorophyll molecule is made up of nitrogen and magnesium. Okay. Do you now understand why all the fertilizer bags say if you want to green up your plant, add nitrogen-based fertilizer? Okay. That's not an untrue statement, but they're going about it from the wrong direction. Okay, because you're going to have chlorosis, which is a lack of nitrogen. Chlorosis shows up, its physical manifestation is yellowing leaves, right? But do you know how many different things cause chlorosis? Not just a nitrogen deficiency. Could be a magnesium deficiency, could be an iron deficiency, could be chilling injury, could be a pest. So the greatest challenge that you have as Master Gardener volunteers is to ferret out What is causing this chlorosis? Chlorosis is nothing more than a symptom. There's 6 different ways my elbow could hurt today. 6 different reasons why. They're not all the same. So when I go to the doctor and say, doctor, my elbow hurts, what's wrong? He starts asking me questions and I get insulted. Why are you asking about my lifestyle? What? No, I don't play tennis. Okay. Yes, I do a lot of pruning. So all of a sudden he's trying to determine what it is that is causing the pain. Right? So chlorosis can be caused by a nitrogen deficiency. Okay? All right, what are the products of photosynthesis? Basic plant sugars. We refer to those as glucose. Glucose is the basic building block. Guess what alcohol is made out of? Glucose. Okay? Sucrose, fructose, all the oses are all based on taking glucose molecules and making them bigger. Right? And oxygen. Those are the 2 products. And this becomes the basic building block for plant growth, glucose. Do you know what kind of ose it takes to make a leaf or a stem? Cellulose. Hundreds of glucose molecules make up cellulose, right? Guess what the other word for cellulose is? Especially for humans. What's that? Dietary fiber, right? So humans don't have the ability to digest cellulose. Okay, that's why it's so good as a colon scrubber, because it runs right through it. The older you get, the more cellulose you should be eating, right? But that is the basic building block that comes from glucose. This is glucose, there's cellulose. So now let's look at the equation. Maybe it'll make more sense to us. Here's the equation. 6 units of carbon dioxide plus 6 units of oxygen equals 1 unit of glucose, C6H12O6, and 6 units of oxygen. What's the energy source? Light. And where does it happen? In the chloroplast. 2 ingredients, 2 products, not reversible. It's a chemical reaction. We good? All about chlorophyll. I love this part. All about chlorophyll. By the way, there's the expanded chlorophyll molecule there on the right. First of all, chlorophyll is light sensitive. Do you know what that means? That means take a plant, put it in the closet, and it's not going to produce chlorophyll. Take the plant out of the closet, and it will produce chlorophyll. Light stimulates chlorophyll production. It has a love-hate relationship with light, because if you put a plant in too much light, the light destroys the chlorophyll. So there's your love-hate relationship. Production stimulated by light. High intensities destroy chlorophyll. Chlorosis, yellowing. That's when chlorophyll concentration goes down. Chlorophyll is a dynamic molecule. Here's my point. This is really, really important when you start talking about fall color. Okay? If you think the same green in your leaves in your garden right now is the same chlorophyll that was there 2 weeks ago, you're sorely mistaken. Okay? A plant continues to produce chlorophyll on a regular basis because chlorophyll has a half-life, if you will. It has a time where it's there, and then it degrades and goes away, and the plant is making more. Isn't it any wonder that the number 1 nutrient that's most efficient in soils is nitrogen? That's because the plant's in constant need of nitrogen because it's constantly making more chlorophyll molecules. Make sense? So it's dynamic, breaks down over time. There's a nitrogen deficiency. Nitrogen deficiency, okay? Chlorosis, yellowing. The only problem is it gets muddier than that, and pardon the pun, but here's a plant that has intervenal chlorosis, which is a classic symptom for magnesium deficiency. We got to know, not only does it turn yellow, we got to know what kind of yellow it's turning in order to assign what the deficiency is. But I think it's really important as gardeners that we understand the factors that affect the rate of photosynthesis. What factors influence? So we back up a little bit and say, okay, what kinds of things influence your ability to bake chocolate chip cookies? Temperature. Let's expand the concept of temperature. How about how big an oven I got? If I have a Susie bake oven, I can't bake very much. I don't care how many ingredients I have. If I have 9 pounds of chocolate chips, flour, water, all that, but I only have an easy bake oven that's only this big, I'm limited by the energy source, yes? Okay. Not only that, but if I'm limited in chocolate chips, if all I have is a half a bag of Nestle's semi-sweet morsels, because I eat them outside of baking chocolate chip cookies, all right, then I'm limited by those ingredients, right? What else is going to influence how many chocolate chip cookies I can bake at any given time? One more thing, it's very important. What's that?
Size of your pan.
Not only the size of my cookie sheet, but maybe how many cookie sheets I have, right? All of a sudden, the availability of the substrate, how much substrate I have. All right, well, if we translate that over, guess what? Our energy source is going to be influenced by or photosynthesis is going to be influenced by the brightness of the light. Light intensity, light duration. Remember our full sun conversation? All of a sudden, now we're beginning to understand why the plant didn't make enough tomatoes, because we put it in 4 hours of full sun. We didn't get the same number of tomatoes you're supposed to get off that tomato plant. I fertilized the mud out too. Yeah, but only 4% of that fertilizer is going to have any influence on the plant growth. You ever see the we'll go a few more minutes and we'll break. Have you ever seen the Miracle Grow commercials on TV back when Richard Whitmark was the spokesperson, right? An old guy that everybody trusted. Right. So he gets up there and he goes, here, use this Miracle Grow plant food and your plants are going to grow better. And then they show a slide and one of the plants is huge. And the other one is, and he goes, the one on the left, you're right, the one on the left was fertilized with Miracle Grow plant food. And the one on the right was not. All the people watching the commercial go, I got to go get that stuff. Right. Are they lying to you? They're just not telling the whole truth, right? So here's the whole truth. The whole truth is both plants were in a position where all other ingredients, everything necessary for plant growth was unlimited. Then, and therefore, that's the only time that 4% is going to be limited. And so the one got fertilizer, and because everything else was unlimited, was able to grow, where the one on the right was like an addition that only had half as many nuts, bolts, and screws it needed in order to manifest itself. Fully, right? But you'll never read that on the bag. You'll never see it on the commercial. Shame on them, okay? But shame on us for not understanding how plant growth works and how nutrition and light influence what we can get out of a plant. First thing I ever ask anybody when they say I have a plant that's failing, I always ask them, what kind of light environment is it in? And guess what? Most people cannot tell me. Do you see where the problem is really? We don't understand the environment we're putting our plants into. All right, water availability. There's an ingredient availability, nutrient availability. Okay, less nutrients, less chlorophyll, less sugar production. Chlorophyll concentration. Y'all, look at this variegated maple over here on the right. Okay, tell me about the chlorophyll concentration in every leaf. How might you describe it? Meager, sparse, right? As a matter of course, does this plant, in order to create enough sugar to grow, require a higher light intensity and duration environment or a lower, typically? Why higher? Because you have less photosynthetic area, right?
Plant can burn too.
It can burn, but in general, plants that are variegated or multicolored in general require a higher light intensity than their straight species that's green. Notice I didn't say that variegated hosta needs to be in full sun. No, the variegated hosta needs a slightly higher light intensity than the straight species that's green, which can grow in about the closet. So that's just a general purpose. Understanding that chlorophyll's dynamic and way too much is going to burn it, right? So, and it's also species specific. Oh, by the way, it's a biological process. Temperature is going to play a role in some way, shape, or form. Higher temperatures, faster, lower temperatures, slower, down to a certain point, up to a certain point. Okay. So here's a variegated Daphne, requires slightly higher light intensities. Yellow leaf plants require slightly higher intensities than their straight species. Same with that burgundy colored redbud over there on the right. So here's the science of foliage color. How on earth can this grow? Well, as I approach it, all the leaves are what color? Yellow. Okay. But if I open up and look inside, what do I see? Green. So here's a plant called yellow saguaro falls cypress, which from a genetic perspective, in full sun, will look like this. But in the shadier locations, the plant actually produces more chlorophyll to compensate for the lack of sunlight. If I planted this whole thing in shade, what color would it look? It would be green, okay? If I put it in a lot of shade, because of its genetics, it would die over time, right? This is not a situation where there's no chlorophyll in these outer leaves. They're just being masked by a high concentration of yellow pigment. Now, the concentration of green pigment in the outer leaves is lower certainly than inside, okay? But it's enough that it will be masked by the yellow pigment. Transpiration is the process where water is absorbed by the plant. We know how that works. Translocated through the plant. We know how that works. And finally evaporated through the leaves. Please understand that transpiration is not equal to perspiration. The water on my forehead right now is slowly evaporating into the atmosphere based on temperature and how many water molecules are in the air. Okay? And it's supposed to be cooling my forehead. In the case of transpiration, water is absorbed, translocated. It comes into the mesophyll, this big area of the leaf, and it evaporates inside the leaf only to escape through these little pores on the bottom of the leaf. There is no cooling that occurs on the surface of this leaf. So this thing called transpiration is not meant to cool the plant. Lots of research has been done to prove that transpiration doesn't cool the plant. However, plant transpiration cools the human sitting under the plant, right? Because it's adding water vapor into the atmosphere where you happen to be sitting, but it's not cooling the plant. 99%, listen, this is so amazing. 99% of all the water that's transpired through a plant, okay? 99% of all the water that's absorbed escapes through transpiration. 99%. That means 1% is used, 1% of the water absorbed by the plant is used in the photosynthetic process. Why would this plant be designed like that? 99% of the water comes up, through, and then out. What's the purpose? What's the purpose? First thing, each and every one of our cells has to be fully full of water to be totally functional. Okay?
Hydration.
That's called hydration. Yeah. And if any of you ever been dehydrated, know that your system doesn't work right. Plants that are dehydrated, their physiology doesn't work right. Okay? And Louise, she's over here yelling, turgor. Okay? Turgor is full cells of water. That's the first thing. And so continuous movement of water through a plant via transpiration contributes to total turgor in that plant, total hydration. Okay? But there's one even more important than that. Anybody here get here this morning via Uber? How do the nutrients get to where they need to be if there's not a flow of water moving through the plant? It is a transportation system for nutrients. It's a transportation system for nutrients. Not only that, but as long as water is moving through and out, these pores are open. You say, well, yeah, they're open and water comes out. Yeah, you know, about 55 gallons per hour on a 50-foot maple tree in the middle of the summer. That's how much water is moving through the tree. I never look at trees the same when I walk outside in the summertime. I'm thinking about for those of you who can't wrap your head around 55 gallons, it's like a full bathtub with no one in it. Some of you are still confused. Okay, a keg. Oh, now everybody understands. Okay. Right, there are three things that influence transpiration. Three things. One, temperature. The warmer it is, the faster the molecules. The faster the molecules, the more water molecules are moving out. Second, relative humidity. If the relative humidity of this atmosphere is low, then water vapor is going to be able to move out more quickly because it doesn't have any competition in the air underneath it, right? And third, air movement. If it's windy, if it's windy, then it's just taking away the molecules that just came out, and that lets more molecules come out. Make sense? All right. So it's May, it's Raleigh. You're going to plant your annuals this afternoon. That's on your calendar. And it's 84 degrees and less than 15% relative humidity with a 15-mile-an-hour wind. Good day to plant, yes?
And sunny.
And it's beautiful sun, not a cloud in the sky. Not a good day, because you are driving that transpiration rate up, and the root system of those annuals that you're planting hasn't even started to become established. It's just not, even if it's a healthy root system, it's just not going to be able to take up the water that's escaping from that plant. So what are the best times to be planting your flowers in the garden? In the rain, 65 degrees, right? Well, if it was on your calendar and you can't change it, then plant in the evening. Plant in the evening, and that's going to give them a little bit of time to recoup. Okay? I've seen some people, I used to do this myself, take big giant golf umbrellas and put them over the plant. You say, why can't you just water them a lot? Watering them a lot is not going to make the roots be able to absorb the water fast. The only thing that syringing will do is slow down the evaporation, slow down the release of water molecules into the atmosphere. Oh, syringing is taking a very light mist of water and putting it out top. Yes, thank you. So let's talk about these little holes, because these are important. The organelle of transpiration. These are electron microscope slides, photographs of the little pores underneath the leaf surface. Called a stomate, plural, stomata. They look like a bagel, don't they? They're a two-celled bagel, and here's how it works. When the plant is fully hydrated, turgor, right? These two cells become engorged, and by being engorged, they create a hole. And the hole is where the water vapor gets out. All right? When the plant loses turgor and becomes less hydrated, these things decrease in size, and the further flaccid they get, the hole closes up, reducing the amount of water that can, you see, it's a self-regulating system. Now here's a little punchline for you. Anybody want to guess what mineral nutrient helps regulate proper stomatal opening and closing? Potassium. Plants that are deficient in potassium suffer from leaf margin burn. Well, no wonder. Their stomates are open when they're supposed to be closed, and they're closed when they're supposed to be open. All right, so there's another, full circle moment there from potassium all the way to stomatal opening and closing. Anybody want to guess how many of these are on the undersides of the leaves per square centimeter? First of all, make a square centimeter with your finger. Okay? Tens of thousands per square centimeter. That's how holy these leaves are. No wonder a maple tree 50 feet tall can transpire 55 gallons of water in an hour. So my question to you is, why? We already established the fact that it's a great transportation system for nutrients, and it maintains good turgor pressure throughout the entire plant. But what's the third and perhaps even the most important one of all? Why all these holes that have to be open? Where does the plant get water for photosynthesis? From the ground. Where does the plant get carbon dioxide for photosynthesis? How does the carbon dioxide in the air get into the plant? Do you understand now why transpiration and photosynthesis are positively correlated, i.e., if all other systems are unlimited, transpiration increases the photosynthetic rate? Well, of course it does, because as long as these guys are open, CO2 is going in just as fast as water vapor is coming out. Okay, so moving right along. We're probably going to now enter into the fifth process of plant growth that is, in general, in my opinion, the most neglected and the least understood. And sadly, the whole picture doesn't come into focus unless we understand this fifth process to a great degree. All right, so what happens to the sugars that are made during photosynthesis? In other words, this photosynthetic process results in ingredients that include oxygen and all this sugar. So what is the plant going to do with all that sugar, all that glucose? All right. Some of it gets stored. Sweet potato, white potato, carrot. Those are all storage organs, and they're storing that sugar that was made during photosynthesis. Some of the sugar is actually going to be used to they're going to become building blocks. They're going to become part of the fabric of that plant. The stem, the root, the leaf, the flower, the fruit, the seed. Okay, all requires a certain degree of building blocks, 2x4s, if you will. Okay, so that's the second fate of the carbohydrate. Biochemical synthesis. This is the one that scares people because it's got two big fancy words. Biochemical synthesis. This is just the plant takes some of the sugar to make some things. Hormones, lipids, proteins, and these are all essential parts of plant growth. Remember, can anybody think of a plant growth process we talked about this morning that we know directly needs a source of energy to work? Active transport of nutrient absorption in the roots. So the roots of a plant need to have a source of energy to be able to take up nutrients. That energy indirectly comes from the sugars that it made during photosynthesis. All right. The fifth process of plant growth is this process right here called respiration. Respiration in plants has nothing to do with gas exchange. Wipe it from your memory banks. Has nothing to do with breathing. Okay? Respiration has to do with sugars that the plant made are burned, yielding chemical energy. You remember your school days, ATP was the acronym that was used to describe a chemical energy, ATP. Guys, here's the cool thing about plant growth. This is, to me, it's miraculous. Plants have the ability to take this kind of energy, light energy, and converts it into what kind of energy is this called? Physical energy or potential energy, all right? And then plants have the ability to take potential energy and convert it into the big E, chemical energy, okay? So really, if we're talking about respiration, it plays a part in energy transfer, right? To a degree that starts with sunlight, turns it into chemical energy. There's no other organism in the world that has the ability to take sunlight energy and make it into chemical energy that fuels you and me. I mean, when we eat a piece of bread, guess what? We break down those sugars and we burn those sugars into chemical energy. That's this. We do it, plants do it. But plants actually do it from stuff they made themselves. We do it from stuff that plants made for us. Right? So this energy transfer apparatus is quite miraculous, if you ask me. So let's put the equation for respiration up on the board. Okay, let's take a look. Glucose, one of the ingredients. What's the other ingredient of respiration? Oxygen. Respiration is oxidizing. We're burning the bread. What are the products of respiration? Carbon dioxide and water. Time out. Bryce, you told us that photosynthesis, carbon dioxide plus water gives you glucose plus oxygen, was a chemical process that was irreversible. And now you just slapped up on the screen a formula that is the opposite. It's photosynthesis in reverse. Why isn't this photosynthesis in reverse? Let me ask you this. If respiration was indeed the reverse of photosynthesis, what would the plant look like when it's respiring? It would give off light. It would give off light. Instead of giving off light, the third product of respiration is, there's the big E again, chemical energy. That's why it's not the reverse. It's close, but that's why it's not. If it were the reverse, plants would be glowing when they're respiring. They'd be giving off light. But instead, they've taken the light energy and made it into chemical energy, which the plant is going to take that and do a bunch of things. I need to make a flower, okay? I need some building blocks, I need some proteins, I need this. Oh, where's the energy to do it? Like, remember my addition to my house? I bought all the ingredients. Bought the 2x4s, the windows, the doors, bought all the fasteners, 4%, nuts, bolts, screws, okay? Went to work, went to NC State, went to work with it. Came home that night, nothing had happened. What did I forget to hire? Contractor, somebody to do the work. Somebody to do the work. So you can have all these ingredients, but if you don't have chemical energy, that plant is not going to absorb nutrients. It can't, because those forklifts run on propane. Fuel, chemical energy. All right. I'm showing you a slide from a book where the person typed and drew arrows in today's digital world, and yet this does it for me. Because just sit back and enjoy this. Okay, seriously, you don't need to be taking notes just because we've talked all about this. Now you can fill in the blanks. There's photosynthesis. Okay, what are the ingredients? Light. That is not an ingredient, but that's the energy source. Ingredients: water. You know where the water comes from. Okay, carbon dioxide. You know where the carbon dioxide comes from. Okay, in the presence of light gives you what? Well, it gives you sugars. All right, and look what happens to the sugars. Some are stored, starch. Some are made into pectins, cellulose, lignin for cell walls. Some of the sugars are contributed to the production of fats, proteins, pigments, hormones, vitamins, alkaloids, etc. All these contribute to all these different substances. And there's some sugar that comes down here and fuels respiration, right? It's the firewood for respiration. Okay, so then we've got respiration here. Okay, respiration, what are its ingredients? Oxygen, we know where that comes from. Sugar, we know where that comes from. Sorry for touching that. Okay, we know where that comes from. So now respiration takes oxygen and sugars, burns them, and gives us energy. And this energy is used for the plant to do all this. Right? Oh, by the way, there's soil minerals. We know how they get in. Soil minerals can't get in there unless there's energy to facilitate the absorption of soil minerals. And between the minerals and the sugars, we end up with all the compounds. That's plant growth. So here's the question. We know what influences photosynthesis: sunlight, duration, ingredient availability, chlorophyll concentration. My question is, what runs respiration? We're all human, right? What happens if we stop eating? Does our respiration rate stop? No, what do? We burn all our fat. Okay. Once the fat's gone, do we stop respiring? No, what do? We start burning muscle. Once the muscles are gone, do we stop burning? No, we start burning our organs. It's a horrible way to die. Okay? But do you notice that the respiration rate continues regardless? Okay? So if a plant doesn't have any extra sugars, will it stop respiring? No. What influences how fast it respires? There's only one factor that influences the respiration rate in plants. What is it? Temperature. Okay. Do you guys understand now why springtime's such a great time for plant growth? Why? Well, because it's warm and sunny during the day and it's cool and comfortable at night, right? Remember, temperature is going to influence how many sugars get burnt. So here's plant growth. Eyes up here, please. Okay, so here's what we're going to do. I'm up against this wall. This is sunrise. Okay, every time I walk forward, that represents the photosynthetic process. So what am I making? What's behind me every time I walk forward? Starts with S, ends with booger. So sun comes up because sugar production only occurs when there's light. Okay, sun comes up, photosynthesis. Okay, what is it? What happens when I step backwards? What is that?
Respiration.
That's respiration. That's burning sugars, right? So in a normal day, I'm a plant. Here we go. Sun comes up. 1, 2, 3, 1. 1, 2, 3, 1. So at the end of the day, the sun goes down. What does this represent? Sugar produced during that day, less what was burnt because of the temperature, right? This is all representative of potential growth. Okay. What if, okay, 1, 2, 3, 1, 1, 2, 3, 2, then the sun goes down. Do I walk forward after the sun goes down? No. Do I walk backward after the sun goes down? Yes. What determines how fast I walk backward? Temperature. So if it's a cool night, springtime, I walk backward slowly, which means by the end of the 24-hour period, this all represents potential growth. What if it's a hot night? Okay. So what happens if at the end of the 24-hour period, I end up here? What happens? No growth, no net gain. Okay. What happens over 6 weeks where I end up here every night, every day? Death. Death. the plant's making exactly what it's burning on a daily basis, and over time it dies. So the question is why? Because if I burn exactly what I make, I don't gain any weight, I don't lose any weight, but I don't die. Plants grow old just like people do. Plants grow old differently than people do. Plants grow old geographically. Can you point to the oldest part of the plant? Yes, you can. Point to the oldest part of you. See the difference? Okay. And so as a result, this branch has leaves, and those leaves, okay, senesce, they get old, right? And so now all of a sudden the plant's got less photosynthetic area to make the same amount of sugar. So pretty soon after, I don't know, a week or two, I'm in the next room at the end of 24-hour period. And so I'm going to end up, right, consuming myself. Do you understand why people who grow houseplants are always stressed over the fact that they're houseplants? They bring them home, they look great, right? They put them underneath a lamp, and they think that's enough light. And after 6 weeks, they start to yellow, and leaves start to fall off, and they start to water and fertilize. And the problem is, every day at the end of that 24-hour period, I'm in there. Do you understand why in the springtime, I'm going to have more net sugars than in the middle of the summer? Now we can start to explain why plants flush and grow really well in the spring, where the days are sunny and warm and the nights are cool and crisp, right? And why in the summertime plants take a small vacation. Okay? Yeah, but what about the tomatoes? You know, even tomatoes stop producing flowers above 86, 87 degrees. Okay. What about these tropical plants? Tropical plants are species whose genetics makes them more efficient at higher temperatures. So it's always going to be related to the species. You can't just blanket say, oh, all plants grow in the spring and you got to. But the point of the matter is we want to make sure we're placing our plants in places where they're making more sugar than they're burning on a daily basis. Okay, at night, the environment doesn't cool off enough for the plant to secure enough sugar to be able to allocate a new leaf. Okay. If I go to coastal Maine Botanic Garden on July 28th, right? By the way, the average summer high in Booth Bay Harbor, Maine is about 76 degrees, and the average summer low is about 57. If I'm a plant, I'm doing the dance of joy. Right? The only difference is I don't have as long a growing season as my friends in North Carolina do. Right? And so there's what do you gain, what do you lose in that kind of a situation? All right. Do you ever wonder why perennial borders in Vermont, Maine, up in New England, they are up on the farm, that in July they're the most colorful, most vivid perennial borders, and my July perennial border looks like somebody sucked all the color right out of it. Okay. Think about it, night temperature, day temperature. Those extra sugars go into there's a sugar-based pigment that contributes significantly to color in flowers and leaves. It's called anthocyanin. It's the same thing that turns your wine red, okay? And anthocyanin pigment is a sugar-based pigment. That means that it relies on extra sugars to be able to be that intense. That's why our burgundy leaf spring leaf plants like redbuds, that's why they fade as summer continues, because the night temperatures don't continue to produce enough sugar to maintain that level of anthocyanin pigment, right? And so we should be okay with our perennial borders looking kind of drab in the middle of the summer, okay? But my perennial border right now looks way better than the one in May, because it's September and mine is still having fun. The one in Maine is shutting down. So that's a seasonal thing. Better fall color when the days are warm and sunny and the nights are cool and crisp. What's that doing? It's contributing to this big, huge sugar pool that's going to be used to make those red pigments. This is why plants grow more in the spring and the fall, because they produce more net sugar because the days are warm and sunny, the nights are cool. So I'm not walking backwards as fast. All right. So if I had to rely on the distance between the wall and me, if I had to rely on that and say, the further the distance, the more resource I have to make things. And every night in the summer, I end up, that's okay, that's fine. I end up close to the wall. What happens to my resources to make things?
But fall temperatures and it's.
But fall temperature is also connected to day length. You see, plants are very, very cognizant. Their leaves are very, very cognizant when it comes to understanding how long the days are. And so by August, they're already being told it's time to shut down. So even if we have warm, sunny days and cool nights, we're still going to get some sugar buildup, but that sugar buildup is not going to be used to make more tissue. It's going to be used to make more color. See the difference? And that's why we can go to the mountains and say, oh, this year's color is going to be crap because it rained so much. Say, oh yeah, the water, you know, it hit the leaves and it washed out the color of the leaves. That's not why. Okay? Every news person, every RAL, the news people say, oh, it's a rainy fall. Wash the leaf. I'm like, no. Send emails, they don't respond. No, what's happening is a wet summer, a wet fall in the mountains, what happens? The daytime temperature doesn't get as high, the nighttime temperature doesn't get as low. So the closer the day and nighttime temperatures are, the less extra sugar is being made. Less extra sugar, the colors aren't going to be as vivid, specifically the reds and the purples. Okay? The yellows and the oranges, they're there all the time. They're going to show up no matter what because the chlorophyll is going to fade, but it's the reds that add that level of intensity. There he is. There's my buddy, Richard Whitmore, not Whitmark, Whitmore. There he is selling Miracle-Gro, right? Light is often the most limiting factor when it comes to plant growth. Fertilizing is not always the answer. In fact, it rarely is the answer. Plant food, not. Okay, this is a misnomer right there, all-purpose plant food. They're lying. They don't understand. 96% of the dry weight is food that comes from the sun. Only 4% is nutrition. This should be called plant fertilizer or plant nutrition. Okay, but this is what you see on TV. This is unfed, that's fed. We have to understand what environments these plants need relative to their ability to grab sunlight and make products out of that. Okay, please understand that shade tolerant plants, they do not respond to higher levels of light intensity to make them grow more. Shade tolerant plants like hosta and hellebores and those, everything's species specific. Everything we've talked about is relative to that particular species and its tolerance and its susceptibilities. It's no different than someone who's incredibly fair skinned with freckles and someone who has more melanin in their, more pigment in their skin relative to how they respond to differing levels of duration and intensity of sunlight. Sugar or sweet. I cut my horticultural teeth as a teenager working at a local garden center. When I say local to New England, I was raised in Western Massachusetts. I got a little job as a car loader at the Hadley Garden Center, and slowly but surely I worked my way up to assistant nursery sales. And so I would wait on customers and whatnot. And I got well trained by the owner of the garden center. And when I went from car loader to fruit tree potter, and then from fruit tree potter to fruit tree merchandising, then from fruit tree merchandising to fruit tree sales, when I got to fruit tree sales, I got to wear khaki, instead of blue jeans and a t-shirt, khaki pants and a green Hadley Garden Center shirt with my name embroidered across the top. That instantly made me, like you will be made, experts when you become Master Gardener Volunteer. Just by virtue of your title, you're an expert. Congratulations. Anyway, so I found myself waiting on customers for nursery products. So I'm standing there one day, there's a man off in the distance. Now we're talking 70, no, not even 77, more like 76, 1976. So a three-piecer, that's what we called them. Okay, back then, you know, businessmen wore three-piece suits, they had this little desk, okay? And this three-piecer, we called him, came walking, and he's walking directly toward me, and he's got his finger out. How can I help you, sir? I bought 3 dogwoods from you people. Well, I've already been trained. I know that when the customer says you people, it's going to be a problem. Okay? So I bought 3 dogwoods from you people 3 years ago, and they still haven't flowered. I want new plants or I want my money back. Pulled a little 3x5 card out of my pocket, and I said, well, let's see if we can get some information. When did you buy them? And he told me the date, and I said, how did you plant them? I planted them exactly the way you told me to plant them. I said, okay, that's fine. I'm going to argue with that. So we started to talk about what he had done with the plants, what might be causing the lack of flowering. The whole time we're talking, this old lady, she was about in her 80s, had a little cane. She was walking behind us, and she was not hard of hearing because she was overhearing the whole conversation. And we're kind of listening and looking up, and finally, she couldn't help herself. She came over and she said, excuse me. Both of us looked down, right? I'm 16. This guy's in his 40s, right? And this elderly woman, she said, excuse me. She goes, I had the same problem with my dogwoods. Well, that got the guy's attention. He said, did you buy him here? I think he was a lawyer. did you buy them here? And she said, oh, yes, I did. And then he looked at me. And I said, well, ma'am, how are your dogwoods? Oh, I got them to flower. So then he looked at her. I said, what did you do? Sweetest little old lady you'd ever want to meet, looked at me and looked at him, and she said, I beat him with a stick. We're like, what? He pulls a 3x5 card out of his pocket and he starts asking her questions. What kind of stick? Was it bamboo? Was it metal? Where did you hit him? How many times did you hit him? When did you hit him? I had lost control. I had nothing to say to this. I'm just kind of going, well, old lady beats her trees, they flower. He's asking her about, I lost it. I'm just standing there going, what do I say? Finally, I had an idea. So I looked at the lady and I said, ma'am, I said, tell me, how are your dogwoods doing today? Oh, they died. They died? Oh, yeah, they just died. Took about 2 years. They died. And he said, even after you kept eating them, she goes, yes. Plants have this incredible ability to select where their sugar goes in their growth process. Okay? And for me to say for them to select helps us understand. But they have the ability to partition sugar for either vegetative growth, leaves, stems, and roots, or reproductive growth, flowers, fruits, and seeds. If the plant doesn't have enough sugar to do both, what's the default? Vegetative. Sure, self-preservation. Biological organism. Self-preservation is, I gotta take my resources and put it to staying alive, right? When a plant is not making enough sugar to do both, and it has defaulted to vegetative growth. By the way, most of your jade plants that people grow in their homes are in that realm. They don't have enough light to produce enough sugar to both produce leaves and flowers. Many people's jade plants in their entire lives never flower. But they're not unhealthy. They just don't have enough sugar to do both. Make sense? Okay, so now you've got this plant in this guy's yard that's just making leaves. Because it's only making enough sugar to make leaves, because that's what it defaults to. And then he comes along with a stick. And he starts whacking that plant in the trunk. How many of you have had plants that are spring flowering flower in the fall for no apparent reason?
Right now.
Yep. Okay. What kind of year did we have? We had a year that was the most incredible spring you'd ever want to see. And then June came and fried everything. Unbelievable stress. And then it rained in July. And then it got hot again. And then it started raining. I mean, this is September and it's cool and it's raining. And September is one of the driest months in North Carolina. And the plants are like, we're gonna die. What do biological organisms do if they fear for their life?
They store energy.
They are going to completely and totally realign themselves to perpetuate their species. That's a biological fact.
Right.
So this plant is going to allocate all its sugar to reproduction at the expense of living for any great length of time, because it's now saying, I'm not going to make the same number of leaves I made last year because I'm allocating sugars to reproducing. Right? So that's why beating it with a stick made them flower. And that's why beating with a stick killed them. All right. So when I asked the woman, and I said, ma'am, how are your plants today? And she said, well, they're all dead. Okay. He just looked at me. So here we are again. So guess what we figured out? He planted underneath a dense grove of pine trees. They were not able to assimilate enough sugar to do both. So they just defaulted to vegetative growth. So he went in, hired a tree company, came in, they thinned out those pine trees, and 2 years later, they were all flowering. Okay? Beat them with a stick.